Hi and welcome back. In today's tutorial we will talk about a popular convolutional network. We will talk about AlexNet. It was designed by Alex Krzyzewski and it was published by Jeffrey Hinton. It is popular because of its high performance back in 2012 when it achieved a top 5 error rate of 15.3% on the AlexNet dataset. The next best result was around 26.2%, which is far behind this network. Now the big question is, how does AlexNet work? Well, it takes an input, a 3-channel images input or a color image, and returns a probability to which class that image belongs to. So looking at the layers here, we first apply a convolutional layer with filter size of 11 × 11 and a stride of 4, and it outputs a shape of 55 × 55 × 96 filters. After that, the next layer is a max pooling layer, and it uses a 3 × 3 filter and a stride of 2. And this layer outputs a shape of 27 × 27 × 96, which then goes again into a convolutional layer and after that into a max pooling layer, which returns a 13 × 13 × 256 filters. After that, it applies 3 convolutional layers with the same parameters as before. The number of filters for the first two will be 384, and for the last one it will be 256 filters. After this, when these convolutions are applied, it moves over to a max pooling layer, which returns a shape of 6 × 6 × 256, which is in total 9216 nodes. After that, it moves on to the fully connected layers, applying 3 layers, which is this part here. The first 2 layers have 4096 nodes, where the third one returns the same amount of units as the amount of classes it has. It applies a softmax function to the output of this layer, and it outputs which one of the 1000 classes the object could be. It is similar to LANet, but much larger. LANet 5 has about 60,000 parameters, when AlexNet has around 60 million parameters, which is a big number of parameters to be learned. But there are some changes that made AlexNet differ from other networks back in the time. Now, the first difference we will talk about is the overlapping pooling layers. Standard pooling layers are summarizing the outputs of neighboring groups of neurons in the same kernel map. Traditionally, the neighborhoods summarized by adjacent pooling units do not overlap. We can see that here. Overlapping pooling layers are similar to the standard pooling layers, except the adjacent window over which the max is computed overlap each other. Also, one big improvement is the ReLU function. A traditional way to evaluate a neuron output is using sigmoid or tanh activation functions. And these two functions are fixed between the minimum and the maximum value, so they are saturating nonlinear. However, in AlexNet, the authors use the rectified linear unit function. This function has a threshold at 0, and this is a non-saturating activation function. And the ReLU function requires less computation and allows faster learning, which has a great influence on the performance of large models trained on a large dataset. And that would be all for the history and how AlexNet works in theory. Now we will move on to the coding part, where we can see how we can implement it in PyTorch. So, I imported all the necessary libraries, like matplotlib, numpy, PyTorch, and I imported some libraries like zip file, shuttle, because we will work with an external database that is called CelebA. And also I imported OS and also pandas. Here I have defined a variable device that will use a GPU or CPU for the training. The first thing we will do here is define a class for the AlexNet model. So AlexNet, and we will use nn.module here. After that, we will define a init function, so init, and we will call self, and number of classes. We will define how many classes it will return, or how many probabilities. We will set it to be 2. So first we will call super on AlexNet self.init. And now, as we mentioned before, it will have a convolutional part and also a linear part. So I will define a convolutional part, convolutional, and it will be a sequential model. And here I'll define my layers. So the first layer, it will be a convolutional layer, so nn.convolutional2d. It will have 3 inputs, so it will be a 3-channel image as input, and it will return 64 filters. So then it will set the kernel size to be 11, stride of 4, and also padding of 2. After the convolutional layer, I will do a activation function, so we will call a value as we mentioned before and set in place to be true. After that we will call the max pooling layer, so max pool 2d, and we will set the kernel size to be 3 and also stride will be 2. After that we can just copy and paste this because it will repeat like this, and just change it so the input will be 64 and the output will be 192. Kernel size we will set it to be 5, and also we will set the stride to be a default value, and the padding will be set to 2. This will be the same here, and after that we will now do the 3 convolutional layers. So I will copy and paste the convolutional layer from here, and the first one will have an input of 192 and output of 384. Kernel size will be set to 3 and the padding will be 1. After that we will apply a rectified linear activation function like this, and then we will repeat this 2 more times because we will need to set the convolutional layer 2 more times like this, and the input here will be 384 and output will be 256, and also 1 more down here, input 256 and output also 256. The kernel size and padding will be the same. And after this we will apply 1 more pooling layer, so max pool 2d, kernel size will set to 3 and stride will be set to 2, like this. And now that we defined our convolutional part, we can now move on and create the linear part. So linear will be also sequential, and I think it will give us an error if we leave these brackets here, so I will just remove them. And also here I forgot to put these here. And now we can move on to the linear layer. So the first layer inside of this part here will be a dropout layer. After the dropout layer we can call the linear or the fully connected layer. It will accept an input of 256 times 6 times 6, and it will output 4096 nodes. And the activation function will be as before the value, and we will set in place to be true like this. And now we can simply just copy and paste this part here and just change it so it's 4096 as input, the number of outputs from this linear layer here, and it will output 4096 again. And after the activation function we will just copy and paste 1 more linear layer, and it will output 2 classes, or the probability for 2 classes. One trick that most people do when working with AlexNet, they define 1 more layer, and this will be a average pooling layer. So we will call nn.average, adaptive average pool 2d, and the kernel size will be 6 by 6. And now after that we can now define the forward pass. So forward, and as input we will place self and the image, so x. First we will call the convolutional layer, and we will call it on x. After this we call the average pooling layer, so average pool on x again. And now before we input our image into the linear layer we need to flatten it, so we will call torch.flatten on x, and the dimension will be 1. After this we can now call the linear layer on x, and we can simply just return x. That will be apply a sigmoid function on that x, like this. And now we can simply run this. We can now call the model, so model will be equal to AlexNet, and run this part also. Now that we have our model, we can now download the dataset. So I will create a directory inside Google Colab that I will call datafaces. And after this, I will download my dataset inside of this folder. So I will call a function wget on this link here. Sorry, wget got in the way. And just run it. I will leave this link in the description so you can download the dataset yourself. After the dataset finished downloading, we can check this icon here, and we can see that we have a zip file, celeba.zip. Now, we imported a function that can help us, or a module that can help us unzip this. So, we'll just call with zipfile.zip file, and we will place the name of the file here, so celeba.zip. We want to read it, so r as zipref, for example, and we can just simply call zipref.extract all and just place the name of the folder that we want to extract it to. So we created one that is called datafaces, and just run this part. When this finishes extracting, we can now see a folder inside this folder that we created. We can now just take all the names of the images. So I will define a variable, a root, that will be the path to that folder. So datafaces, image align, CelebA. And now I will define a variable, image list, that will store all the names of the images. And using the function os.listdir, this will list out all the images inside of that folder. So we'll just pass in the root. And we can simply just print out the length of the image list. And we can see that we have 202,600 images. Now, the next step would be splitting the images that we want to classify our model on. So we want to, for example, classify smiles and no smiles on these images. So we have this many images. How do we classify, or how do we pick those that have a smile or don't? So we can simply just go here and type in CelebA Kaggle and click on the first link. And if we scroll down here, we can see these CSV files. We will just download the first one, list attribute CelebA. Click here and it will start downloading this CSV for you. When it finishes downloading, the next step would be extracting that CSV file, and I already have it here extracted, so I will just drag and drop it here and wait for it to be uploaded. While we wait for it to upload, we can start coding the part where we will load this CSV file. So we'll call it df for data frame, and we'll use pandas read CSV to load in that file. So just place the name of the file here. And now if we print out df, we can see that it still didn't load all the images. So it needs to load it even more because it is still uploading. But now we can see that it has a lot of attributes, and we want just the image ID and the smiling column. So we will just select the image ID and also smiling, like this, and just place it into a df. I will just change the df so it's this, like this. And now when it uploads, we can simply just rerun this part here and also this part here, and we just print out the df. We can see that we have all the attributes for our images. Now, the easiest way to rearrange these is by creating a folder that is called, for example, data, and inside of this folder we will define two more folders, or create two more folders. One is smile and the second one is no smile. And now the next step would be classifying or rearranging all of these images inside of these two folders. So we can do this by creating a for loop for I, then I row, because we will iterate through all of these rows in enumerate of daf.iter rows. This will iterate through all of the rows. And now we want to specify not all images, we want, for example, 1500 images. in each of these folders. So we will define a variable num, and it will be 1500, and also S0 and S1, and it will be set to 0 and 0. Now we will ask for each row if S0 is less than the number. Then we will ask it if I row of the smiling is equal to 1. If it is, then we will add to S0. And also we will copy the file. By copying the file, I mean to copy the image. By file, I mean image. So one way to do this is using the shuttle module that we imported and using the copy file function. We just specify the file that we want to copy and the path there where we want to copy it to. So we want to copy it from data faces, image, align CelebA, and the name of the file is iRow image ID, and where we want to copy it is data, and if it is smiling is equal to 1, then we will place it into the smile folder. So iRow image ID. And we can do the same thing now for the no smile folder. We'll just copy and paste it here and just ask if S1 is less than the number, and if smiling is equal to -1, then S1 plus equals 1. And we will just place it into the no smile folder. And because we want to break it after a certain amount of iterations, maybe we don't need this. Yeah, this is okay. Now we can simply just run this and wait for it. Okay, we have an error here. So I forgot, we need to place here this here and also here. So because this is a folder. And then run it. When this finishes, we can now create the image list variable again, rearrange some values. So os.listDir data smile, and then we will simply append or extend this image list with the os.listDir data no smile, and just print out how many images we have. So len of image list, and we have 2,999. Now after this we can now simply load our images. And the way we are going to do this is by using the Torch Datasets module. So we will call CelebA data, and we'll call datasets.imageFolder. This function will go in every image or in every folder, and the folder name, for example, no smile, will be a class, and smile will be the second class. So we'll just specify the path, so it will be data, and we want some transformations applied. So before this, we will call transform and transforms.compose, and the transformation that we want to apply is, for example, a resize. So transforms.resize, and we will set it to be 64 by 64, and also we will transform it so to tensor, like this. And then inside of here, transform is equal to transform, and just run it. Now we can simply check out the classes, what I mentioned earlier. So we can just simply print out CelebA data.classes, and also print out the len of this dataset that we loaded. And here we can see that we have no smile and smile. This is a folder, a hidden folder, so we need to remove this folder. And one way to do this is by calling remove rf and specify the path to that folder that it created. So it will be data, and the name of folder I will just copy it and paste it here and just remove it, and then rerun this part here to load in the dataset. And now if we run this, we have two classes, no smile and smile. And now, because this is all stacked onto each other, we can now split this into training and testing. So train set test set will be torch.utils.data.randomSplit. So this will split our data, and the way we are gonna split it is by 75% to 15%. So what we want to split is CelebA data and inside of this we will pass in what where we want to split it. So how many images will be used for testing and how many for the training. So for the testing we will use integer len of the image list. So I can do this above here, so I will just take this and place it here. So the train size will be the integer of the len of the image list that is multiplied with 0.75. And then for the test set, so test size will be the training size. So we will just take this. We will take the len of the image list subtracted by the training size and just simply print out the training size and test size. And this is our split. So we can just simply here place the train size and also the test size. And then simply run this part. Now we can say that our data is processed. Now we can move on and start training our model. So we first need to define the optimizer and the criterion. So optimizer will be optim.atom. And what do we want to optimize? Of course, the model.parameters. And the learning rate, we will set it, for example, to be 0.001. And for the criterion, we will be using the cross entropy loss. And run this part. And I forgot here to create the train and test loader. So we will simply create training loader and the test loader as before. So the train loader, we will call torch.utils.data.data loader. And I will copy and paste this down here and specify here the training set, the batch size. I will set it to be 64 and shuffle equals to true. Just copy and paste this here and change it so this is here the test set and run it. And now we can move on to the training. So we will train it, for example, for 10 epochs. We will save the training loss into a list, and then we can move on to the training. So for epoch in range of epochs, total train loss will be set to 0, and then we will start the training. So for index image label in enumerate the train loader, so this will go through every batch, and we can simply now call optimizer.zeroGrad to zero the gradients. We can call the model on the image or the 64 images. And then we can calculate the loss, criterion, prediction, and also the label. And down here we can now append to the total training loss for this batch plus equals loss.item. And the last step here would be calling the backward and optimizing the parameters, so optimizer.step. After it finishes this for one batch or for all the batches, we can now calculate the training loss. So total training loss will be total train loss divided with the index plus 1. And then we can append to the training loss the total train loss. And then we can train our model. Just run this part here. This may take some time depending on your specifications of your computer, but now it finished training at my, so I'll just plot the loss so we have a better understanding of what was happening. So we'll plt.plot training loss, and we can see that the training was dropping. So it would drop even more if we pumped this number up, the number of epochs, but you can do that yourself. You can experiment with this number, also the number of epochs, and the batch size, learning rate, and see what you get. So we will stick with this one here. Now we want to test our model. So the one way to do this is by creating a test iter variable and iterate through the test loader. Just take out the first batch, so images and labels of the test iter.next. So this will take out one batch of images. So I have an error here, so it is equals and like this. Now I want to test my model on 50 images, for example, and see how it does on those 50 images. One way to do this is by turning off the torch.noGrad to turn it on, so it doesn't calculate the gradients anymore, and just create a prediction, so call model on those images. Run this. If we check out the shape of this prediction, it should be 64 predictions, yep. And then we can just simply take out every image. So one way to do this is by calling images numpy i.cpu, so this will iterate through all of the images in images. And also we will select the class names, so class names will be CelebA Data.classes. Now if we print out the class names, we should get smile and no smile. And now I will copy and paste one piece of code here from the previous video. Here I have created a figure and I have adjusted my subplots on that figure. I will take 50 images and add subplots based on the I or on the index. I will show each image, so images numpy, we extracted them here. I will permute them because now the shape of this image is, for example, 3 times 64 times 64, and this permute will make it 64 times 64 times 3. For example, it will grayscale it. And this part here, so we will ask if the labels of I, so the original label, is the same as the maximum probability in those predictions. If it is, then the color will be blue. If it is not, then the color will be red of that label or of that text on that image. And I will just run it. And here we get our grid, so we can see that it got most of them correct. For example, these are all correct. It missed this one here, these two here, this one, for example, this one, but most of them are correct after only 10 epochs. Now I will leave this collab link in the description below so you can get a copy of this yourself. So one way to experiment here is by changing the number here. So if you want more images, for example, you can select here, for example, 3000 images, 4000, how many images you want to select for the training and testing. And also you can change the attributes. You can go over the file, this file here, and see what attributes it has. Also you can change the test and training size. You can experiment with the learning rate, the batch size, and so on. And that would be all for this video. If you like this video and you found it helpful, drop a like and subscribe to our channel. If you want to learn more and read more about AlexNet, I will leave a link for the blog post in the description below. Thank you for watching, and as always, be safe.